Western Electric, 30 years ago, before solid-state electronics and transistors. From factories like this came a nationwide switching network connecting millions of telephones. If only two phones existed, only two wires would be needed to connect them. 10 phones would require 90 wires to reach each other, if no switching means were available. The 85 million phones in actual use today would need an astronomical number of wires without an adequate switching system. The switching network built by Western Electric includes over 10,000 major switching centers that enable any phone to reach any other phone using the minimum number of channels. The network has served and grown without interruption for nearly a century. New products and techniques have kept it up to date, always working. Today, the electronics revolution has transformed manufacturing. New kinds of challenges confront communications scientists and engineers. To make today's components, they must probe matter more deeply. To solve problems of material characteristics, to deal with temperatures from 200 degrees below to 2,000 degrees above zero Fahrenheit. They must create new materials and shape them on a molecular scale. This requires new tools, new processing techniques, an entirely new manufacturing environment. Precision is essential at every step in processing and measurement. Microscopes and instruments extend the capabilities of eyes and fingers, increasing skills. Atmosphere must be controlled, from tremendous pressures to a high vacuum previously found only in space. And dirt and dust must be excluded. Sometimes light and color must be controlled. From this new environment is now emerging the hardware of an important development in communications. Number one, ESS, an electronic switching system. Designed by Bell Telephone Laboratories, ESS is manufactured by Western Electric for the Bell system to meet the challenge of expanding telephone needs. ESS represents a radical advance in making telephone connections. Virtually all electronic, it uses magnetically stored information to control the operations necessary to put through a call. An incoming call is detected by scanners, which report it to central control. Central control routes the number being called into a temporary memory unit, where it is held. Then, using the semi-permanent memory unit, central control determines whether the call is local or long distance, and what lines must be used to make connections. This information is contained in magnetized memory cards that function somewhat like punched cards used with business machines. The cards can be easily removed for alteration of the information. When central control has obtained all the data necessary for completing the call, it issues instructions to the switching network. The network, together with circuits that lead to trunk and local lines, performs the physical functions that connect the telephones. The time from the moment dialing is completed to the moment the called number rings is a small fraction of a second. ESS offers uniquely flexible, convenient service. It can transfer your calls to another phone when you're away from your own. If you're busy talking, it can automatically signal you that another call is trying to reach you. It can set up conference calls. And dialing just a few digits will connect you to numbers you call frequently. The key to these services is stored program control. Heart of this control system is the semi-permanent memory unit, called a twistor module. In its manufacture and assembly, new processes and tools are being developed to assist human skills in achieving greater precision and uniformity. Access to information stored on the memory cards is provided by special twistor wire. To make this wire, a thin permalloy tape is wrapped in a spiral around a small copper wire, thinner than hair, at 12,000 revolutions per minute. The tape itself is formed from wire under a pressure of 1 million pounds per square inch. Any dirt or imperfection in the metal, even a 10,000th of an inch in size, can ruin a complete memory unit. "45 twistor wires, along with accompanying conductor wires, are embedded by heat between two mylar polyethylene belts. Wire placement is checked in the finished cable. During the early years of manufacture, electrical test records were kept on every 1,000th of an inch of twistor wire, allowing a check on later performance. Here, as in most ESS manufacture, quality depends on precision. When the twistor module is assembled, twistor wires line up at right angles to copper straps, which function as solenoids. There are more than 300,000 intersections in each memory module. Not one wire can vary in position more than 3,000ths of an inch. A typical ESS program store includes 16 wired modules, with a capacity of nearly 6 million information bits. More than half are used for self-checking maintenance programs. The rest used for more versatile switching programs than is possible with the electromechanical system still in general use. Another high production component, the sealed contact. This is the basic element of the ferried switch that performs line switching functions in ESS. Millions of such contacts will be needed every year. From preparation of the iron-nickel reeds to final assembly, mechanized processes are brought into play. There have been many production problems to solve. Not even a speck of dust 1,000th of an inch in size can be tolerated. Also, the reeds are soft after annealing. Human handling had to be avoided. The solution? Loading and transporting the reeds in racks through gold and silver plating to chemical and ultrasonic cleaning. pair of reeds are sealed under pressure in a small glass capsule. Production problems must be solved every day. For example, unstable contact resistance. Its causes were not fully understood, especially in the early stage of manufacture. But the facts leading to a solution are coming from constant research and testing. The ferried switch, which uses sealed contacts, represents a great advance in switching. When performance and economy become competitive, further advances will probably come from solid-state technology. Here is a world where material is grown into crystals with controlled impurities, with intolerances which are molecular, even atomic. The objective? Semiconductors, transistors, and diodes needed by the millions for ESS offices. Bell Laboratories' invention of the transistor and its later work in semiconductors made the basic concept of electronic switching a practicality. This single silicon crystal will be trimmed, then sliced and diced. These slices have been cleaned in a liquid by means of ultrasonic energy. A special technique, called epitaxial deposition, involves the growing of molecular layers in an oven to extend the originally grown crystal structure of the silicon slices. Control of temperature is critical. It must be uniform across the slices. Materials such as boron and phosphorus are diffused into the silicon to provide desired electronic characteristics. This diffusion is measured in parts per billion. Patterns are made by a photographic process and then micro-machined by chemical etching to produce nearly 1,700 transistors on each slice. Testing and measuring are continuous for resistivity, for thickness. These are controlled to rigid specifications to suit many applications. Hundreds of solid-state components nearly ready for cutting. New processing techniques are increasing semiconductor production rates as well as improving quality and reducing unit cost. As solid-state manufacture becomes increasingly sub-miniaturized, problems multiply. For example, in attaching leads. Gold wire, 1/1000th of an inch thick, is joined to thin aluminum electrodes that have a bonding area only a few thousandths of an inch square. Connections are made at a rate of 400 transistors per hour. Semiconductors must meet reliability and performance requirements matched only in missile and space technology. To assure uninterrupted service, major ESS units are duplicated in each installation. Alternate routing is accomplished in microseconds. There is a continuing challenge. Increase the production rate of ESS units to reduce costs and at the same time improve unit quality. The challenge can be met by improving design and manufacturing techniques. In the case of the ferried switch assembly, a newly developed concept makes it possible to wind 64 coils in one continuous operation. Mechanized processes such as this are expected to increase ESS frame production at a very rapid rate within the next decade. There are many specific manufacturing challenges. Operations such as wiring the ferrite memory module depend on human skills supplemented by training and expert supervision. Manufacturing a complex system is accomplished by dividing the process into many separate operations, such as this. Intricate yet compact circuits allow ESS to check itself continuously, report a change in component performance that may lead to failure, and direct replacement of the suspected unit. Faster switching and continual self-maintenance enable an ESS office to process many more calls than previous electromechanical systems, while requiring less space. Somewhat like a teaching machine, a wiring assist device uses punched tape, which causes a sequence of lights to direct the operator's work. In all areas of ESS manufacture, solving production problems has required a new look at the skills of people and machines, a search for the best ways to combine them. Human sensing, judging, and tactile abilities often provide a more suitable solution to a production problem and can be offered by the most complex machinery. ESS units are designed for a minimum of interconnections at the final installation, so that most of the wiring and much of the detailed testing can be done at the factory. Thus, manufacturing responsibility extends far beyond the making of parts to include integrated construction of an entire system. This manufacturing experience has already led to even more sophisticated processes and devices that may find application in future systems. One of the most promising developments, thin film circuits. In a unique moving line vacuum chamber, pure metal is deposited on glass or ceramic plates in a film only 4/millionths of an inch thick. Using an emulsion sensitive to ultraviolet light, photoresist processes generate circuit patterns. The negative design permits certain areas of the plate to be exposed. The pattern is varied according to the desired circuit application. The exposed area is etched off. Greatly magnified on a shadow graph, a resistor pattern is checked for precision. Each plate contains 54 complete resistors and interconnections. These thin film resistors can be adjusted to close tolerances. They're extremely stable and economical to manufacture. Contact areas for leads are deposited by a sputtering process. The basic goal, whatever the product, make it smaller, more reliable, more economical, extend its function. Beam lead and multiple chip circuits are a step toward fully integrated circuits grown into a single block of semiconductor materials. This is the threshold of electronic telephone switching. In the years ahead, electronic central offices will bring new and better kinds of service to the telephone user.